In this video, I'm going to discuss elementary matrices and some basic results derived using them. I've summarized the results that I'm going to discuss here, and I'll pause for a second so that you can maybe, if you wish, pause your video to read them. All right. To begin with, I'm going to define a few definitions. A non-singular matrix is any matrix, is a square matrix which has an inverse. An elementary row operation on a matrix consists of either interchanging rows, multiplying by a row by a constant, or replacing a row by the row plus a constant times another row. Then an elementary matrix is, by definition, an elementary row operation operating on unit matrix I, and then it's easy to show that elementary row operation on A can be achieved by the corresponding elementary matrix multiplying A. Now I will be using two different variations of matrix multiplication, and I'm going to illustrate them here. In the first, I'm going to multiply scalar rows times a column of row vectors, where the first row, for example, is 2 times A, 3 times B plus 2 times C. The other variation, I'm multiplying columns of scalars times columns of row vectors, where the first column, for example, is 2A plus 5B plus 3C, and the second column is 3, etc. I'm going to use some abbreviations: NS, non-singular; LI, linearly independent; R rank, RRCR, row rank, and column rank. Now, for the first theorem, I'm going to show matrix is non-singular if and only if it has linear independent rows. If A is non-singular, then the only solution to AX equals 0 is x equal to 0, which I get by pre-multiplying by a to the minus 1, which exists because A is non-singular. If A is linearly dependent, then A is non-singular. If A is linearly independent, AX equal B has a solution for all B. In particular, it has a solution for x1 equal E1, x2 equal E2, which I can write in one equation as A times the matrix x1, x2, xn is equal to I, or AX is equal to I, and therefore A is non-singular because it has the inverse x equal to a to the minus 1. Now, every elementary row operation has an inverse. That's almost obvious. The inverse for multiplying a row by k, the inverse to that is multiplying a row by 1 over k. Now, elementary row, this is an important theorem. Elementary rows operations don't change the row rank or the row space. Now, suppose I have a matrix A and I multiply it by an elementary row operation to get M. So M is equal to ERA. Then A is equal to ER to the minus 1 M. From this, I see that the row space of N is a subspace of the row space of A, and the row space of A is a subspace of M, so that the row space of A hasn't changed. Row space of A is equal to row space of M. Then, since the row rank of M is less than or equal to the row rank of A, because M is the rows of M are linear combinations of the rows of A. Remember that multiplication we did? And the row rank of A is less than or equal to the row rank of M. From this implies that the row rank of M is equal to the row rank of A. The product of non-singular matrices is non-singular because AB, B to the minus 1, A to the minus 1 is equal to I. And then a more sophisticated theorem, any non-singular matrix is a product of elementary matrices. So if I have A is equal to this, then because A is non-singular, the first row can't consist of all zeros. So by elementary row operations, I can change the first column to 1, 0, 0, 0. Now, and this is an important point because if E1, since E1 and A are non-singular, their product is non-singular, which means the second column here can't be all zeros or just an X up here and 0 here. That would make it linearly dependent. So it means by elementary row operations, I can put the second column in the form 0, 1, 0, 0. It has a non-zero X in this section here. So I have E2, E1. Again, A equals this. Again, this is a product of non-singular matrices. Therefore, the third column can't be all 0 or a linear combination of the first two columns. So it has to be of the form 0, 0, 1, 0, after which I can put into, I can put it in the form 0, 0, 1, 0 by elementary row operations, E3. So the final result is that a product of elementary matrices times A is equal to I, or A is equal to e to the minus 1, which is a product, which is also a product of elementary row operations. All right. Now we get to some more complicated stuff. Excuse me. If any matrix A can be put in the form of a column matrix consisting of the first linearly independent columns of A times a matrix reduced row echelon form. So this matrix of linearly independent columns can be expanded to a square matrix by adding arbitrary columns that are linearly independent of the columns in C to come up with a non-singular matrix, because the columns are all linearly independent, which I call E. And then I can to get the same result as this. I have expanded E. Now I have to add some zeros down here to take care of the extra columns that I've added here. And that follows from the column operation I've shown. So that finally, I wish to point out that the starting position of for this, and my position is that the reduced row echelon form is the result of factoring out linearly independent columns from A. And that once you have done that, you can also arrive at reduced row echelon form with a 0 down here by elementary row operations. So this reduced row echelon form, found by factoring linearly independent columns, can also be arrived at by multiplying A, well, in this case, multiplying A by the inverse of E. In other words, by elementary row operations, you can also arrive at the reduced row echelon form as defined by column factorization. Whew, hope that something survived all of that. All right. Now, as an example of that, as an example of that, I'm going to say, suppose A is equal to column 1, and I'm going to call it one of the linear independent columns because it's not equal to 0. Then A1, which is linearly dependent on C1. Then another linearly independent column. Then another linearly dependent column, A2, which linearly depends on C1 and C2. So then I can write this as C1, C2 times 1, 0. Note that 1 times C1 plus 0 times C2 gives the first column of A, plus this next column, which is linearly dependent on C1, so it has the form X0. So second column of A is X, some constant times C1. Then I have the next column of A is C2 times, is C1 times 0 plus C2 times 1 is C2. then the final column of A is X is a linear combination of C1 and C2. So I can write that as A is equal to C times reduced row echelon form. In this case, there are no zeros. Next, the next theorem is that row rank is equal to the column rank, and that's because the column rank of A is equal to the column rank of C by construction, and the column rank of C is the column rank of the reduced row echelon form. It's the pivot, the rank of the pivot given by the pivot columns. This and this correspond to this and this. A reduced row echelon form, and the column rank of reduced row echelon form is equal to the row rank of reduced row echelon form, which is equal to the row rank of A. That's the row rank of reduced row echelon form, row rank of A. That's a little bit tricky. The reason for that is I can write from this equation here, I can write that the rref0 is e to the inverse times A. And e to the inverse is a series of elementary row operations on A, which do not change, elementary row operations don't change row rank. So the row rank of rref is the row rank of A, which proves our row rank is equal to column rank. T3 prime, now because row rank is equal to column rank, T3 said that an elementary row operation, doesn't change the row rank, but the row rank is equal to the column rank, so therefore an elementary row operations don't change column rank or row rank or the row space. Now I have that a matrix T1 prime, it's a matrix if it has linear independent, non-singular, if it only has linear independent rows. Now, because row rank equals column rank, a matrix is non-singular if and only if it has linear independent rows or columns, and that the corollary to that, if A is non-singular, so is A transpose. The next theorem is significant but fairly straightforward. If A equals BC and B is non-singular, then the rank of A is equal to the rank of C. That's because the row rank of A is less than or equal to the column rank of C. If I multiply C is equal to then if I write C is equal to B to minus 1A, then the row rank of C is less than or equal to the row rank of A, in which case the row rank of A equals row rank of C, row rank equals column rank, R of A equals R of C. And if C is non-singular, A transpose is equal to C transpose, B transpose, and proceeding similarly and using that row rank equals column rank, you get that the rank of A is equal to the rank of C. Now, this is an important theorem, C9, which I had trouble finding on the internet, and that is the recovery theorem, which is given rref, what is the matrix A that it came from? Excuse me. Well, in this case, if C is a matrix of L linearly independent columns, any C which is a matrix consisting of L linearly independent columns and of any length, M is arbitrary, then C, that matrix C times rref, which we were given, gives you the matrix A, which has the reduced row echelon form of that. All right, so that's recovery. Now, another heavy-duty theorem here is that the solution to AX equal B and AX equals 0. Now, AX equal B and AX equal to 0 if and only if EA times X is equal to EB and EAX is equal to 0. So, and the solution to this is the solution EA is rref0, X is equal to EB, which is equal to D0, so that, or I'm going to ignore the zeros down here, which play no role. The solution to this is the solution to rref xp is equal to D. And the solution to this, correspondingly, is the reduced row, which is for the null equation for the null space. The reduced row echelon form x sub I is equal to 0. Now let the reduced row echelon form times E equal IF, where E is a product of column matrices that rearrange the columns of the reduced row echelon form into IF. For example, E might be the elementary matrix which interchanges, for here, E would be the elementary matrix which interchanges columns 2 and 3, so that this times E would give this in the form IF. All right, and now RREF equal, all right, and then I'm going to solve using IF. I'm going to solve the equations IF times XP prime is equal to D, and IF times X prime, where now X is the null space matrix consisting of columns that satisfy IFX equals 0. All right, now if I do that, then having solved this, these two, as follows: XP prime is equal to D, and X is minus Fi, because IF times the matrix minus Fi is minus F plus F is equal to 0. So I've solved the equations IF X IF reduced to echelon form IF X is equal to D and 0. All right, but I need a solution to RREF X equal. So what I do is I'm going to replace IF, this reduced row echelon form IF, by the original reduced row echelon form times E, by this definition here. So then I have RREFE times XP prime is equal to D, and I have reduced row echelon form of, again, EF X prime, IF, the reduced row echelon form, IF is the original reduced row echelon form times E times XC prime is equal to 0, from which the solution to RREF XP equal D is XP is equal to E XP prime, and the solution to RREF XI equals 0 is XC is equal to E times XC prime. Now that's going to make a lot more sense if I take if I deal with an example. So I'm going to consider this example now. Solution of AX equal B. Now the solution of AX equal B is the solution to EAX equal B, and that becomes RREF0 X equal D0, which is this solution is exactly the same as the solution RREF X equal D. Now the RREF0, for example, could be this, and that's equal to D equal to 790. And that's exactly the same solution as this RREF X is equal to 7/9. Now, the reduced row echelon form RREF times a product of elementary column matrices, column interchange matrices, will give IF, which is this, and IF is equal to this, which gives IF is equal to this, the original RREF, and E23, which interchanges, it is the elementary column matrix which interchanges columns 2 and 3 to give this equation, IF. All right, now, if xp prime is equal to D, if IF, now the equation IF xp prime equal D is the equation 10 times xp prime, which is 79000, equals 79. So this is xp prime. IF xp prime equal D is this equation, and this is xp prime. And then, therefore, xp is equal to E23 times xp prime. Now, E23, which was a column interchange, becomes a row interchange if you pre-multiply. So xp becomes E23 times xp prime. So originally, EP said interchange columns 2 and 3 to get IF. Now, you get to go back, interchange rows 2 and 3 to get interchange rows 2 and 3, interchange rows 2 and 3 of xp prime to get the solution of RREF xp is equal to D. So that's the solution. Okay. Now, I have, if I have the equation IF x prime is equal to 0, we have that solution IF is minus Fi, and IF is equal to this. Therefore, x prime is equal to minus Fi is equal to this. Minus 2, minus 3, minus 1, minus 0, minus 2, minus 4, 1, 0, 0, 1, 0, 0, 0, 1. So, reduced row echelon form times IF, all right, IF is reduced row echelon form times E23, and that multiplied by x prime will give, x prime will give 0, because I times x prime is equal to 0. This term is I. So RREF, the original RREF, times E23 times x prime, now pre-multiplying by E23, interchanges rows 2 and 3 of x, so that E23 x prime becomes minus 2, minus 3, minus 1. Interchange rows 2 and 3, 1, 0, 0, 0, minus 2, minus 4, 0, and then 0, 1, 0, 0, 0, 1. And this is the solution. So finally we have that this is the solution to AX equal B, and this is the solution to AX equal 0. You're going to have to give that a little thought. That's probably worth a video. That whole, just this T10 is probably deserves a video. I hope some of it got through. All right, now finally I'm going to say a few words about determinants. Namely, I note that if E1, E2, and E3 are the interchange multiplied by K and add K times another row, then this is a simple check. Determinant of E1 is minus 1. Determinant of E2 is K. Determinant of E3 is 1. And it's easy to show that the determinant of ER transpose is the determinant of ER. So from that now we can show that the determinant of ER times A is the determinant of ER times determinant of A. And you just have to look at the individual cases to show that. For example, if ER is a row interchange, then determinant ER times A interchanges a row of A, so that it's determined now. So now this determinant of ERA is minus 1 times the determinant of A, but minus 1 is the determinant of ER, so that determinant of ERA is determinant of ER times the determinant of A, and you can check that yourself for the other two cases. So now the two important things that come out of this are, first, or the most important thing that comes out of this is, first of all, that the determinant of A times B is the determinant of expressing A and B, because we can express any non-singular matrix as a product of elementary row operations. So the determinant AB is the determinant of E1, E2, say for A, and E3, E4 for B. And that determinant is, by this, is determinant of E1 times determinant E2, determinant E3 times determinant E4, which is determinant of A times determinant of B. And the last one, which turns out to be easy, but in the past it gave me a lot of trouble. As a matter of fact, I did a video on just this, and I might erase the video because it's so simple here. I have that the determinant A is unequal to 0 if and only if A is non-singular. Now, if the determinant of A is equal to 0, AX equals 0 has the only solution x equals 0, and so which means that the columns of A are linear independent. Got on to subconsciously another thought, which means the columns of A are linear independent, or A is non-singular. On the other hand, if A is non-singular, then A is a product of, I can prove that in one of two ways. Either A is a product of elementary matrices, or A times, it's non-singular, has an inverse, A times H minus 1 equal I. And in either case, the determinant of A is unequal to 0. Thank you.